Now, a quantum is what we know of as subatomic matter, so what the atoms are composed of. We refer to them as photons, neutrons, and electrons. And within an atom, they can take on different positions, and they adhere to a wave-particle duality. More on that later. Now, Heisenberg's uncertainty principle states that for a quantum, we can only measure one of two things. We can either measure its position with certainty, or we can measure its momentum or velocity with certainty. The more certainly we measure one of the two, the more impossible it is to measure the other one. And this applies essentially to all, not just to quantums, but to all wave-like systems, but is a fundamental principle that is also at the base, for instance, of superposition.
Right. So a quantum superposition is the fundamental principle of quantum mechanics, where any two quantum states can be added together and the result will be another valid quantum state. Now, to explain this, this principle has been proven in many different experiments. One of them, or the oldest one, is the Copenhagen interpretation of quantum mechanics by Niels Bohr and Werner Heisenberg from 1927. And they say that quantum mechanics can only predict the probability distribution, not the exact measurement of a quantum state. So it's just about the probability distribution, what you can expect, and not the exact measurement. And that's because quantums don't have these definite properties before being measured. And the interesting thing, as you mentioned before, is that these quantums are both particles and waves at the same time. And this is known as the wave-particle duality. And this has been shown in some well-known experiments. We'll get to one later. And this is this is known as the superposition, where you have a quantum that is in two states simultaneously, and they resolve into one state or collapse into one state once we observe or measure them. So our very observation of a superposition forces it to create reality, as it were. And so the famous experiment is known as the double slit experiments. And here you basically shoot a photon through a metal slit, and it's shot as a particle initially, but ends up as a waveform at the wall behind the metal. And this demonstrates its superposition, in that its resolution into one of the two states only occurs when the result is observed. This idea of existing in two states and only being forced into one once it's been observed is probably the most, it's probably best known in the Schrodinger's cat experiment, a thought experiment from Erwin Schrödinger that he mentioned in discussion with the famous Albert Einstein, where you place a cat into a sealed box along with a flask of deadly poison and a radioactive source. Now, the poison is released only when the internal monitor detects radioactivity. Radioactivity is only detected as a wave. Yet, according to the Copenhagen interpretation, due to the wave-particle duality, the radioactive source is both particle and wave at the same time. That means because it's a particle, radioactivity isn't detected. But because it's simultaneously a wave, it is detected. So this means that you have two outcomes simultaneously. You have the poison being released and the cat dying, as well as the poison not being released and the cat being alive, which means that the cat is dead and alive at the same time. But it's only resolved into one of these two states, meaning that only when we observe does the radioactivity decide on whether it's a wave or a particle, and subsequently whether the cat is alive or dead.
So yeah, quantum mechanics is really spooky. In fact, so spooky that for the other principle, entanglement, Albert Einstein, the man himself, said spooky action at a distance. Now, if we split, for instance, photons, if we have two entangled photons, theoretically, it does not matter how far off they are from each other. When they are entangled, if you spin one of them, the other will spin two. And this happens faster than the speed of light. So I think several hundred times faster than the speed of light. Now, the idea is when you have an interference of quantum entangled particles, which you have in an extension of the double slit experiment, which essentially mean that you split the photon prior to sending it through the slit. And what happens if you observe one of the two, the interference pattern that you would expect to occur at the wall behind is not going to happen. For the very reason that you observed one of the photons. So this means that the observer, him or herself, actually has an impact on the result. Now, an interpretation of this is even if you observe the outcome in the future. So even if you observe one of the photons in the future, the other photon in the past is going to decide not to be a wave. Which is pretty crazy to think about. And this is how far our understanding goes. So there's a long way to go still when it comes to entanglement. But the properties of it, we can partially already use today, and they will prove to be very useful for quantum computing. Another one is quantum tunneling. And quantum tunneling is a principle that refers to the fact that waves can pass a physical barrier that is not thicker than somewhere in between 1 to 3 nanometers. And so instead of surmounting the obstacle, instead of having to go over the barrier, it can simply pass it. It can pass through it effortlessly, which is another useful property of quantum mechanics for quantum computing. And where it gets not just spooky, but somewhat futurist and crazy is teleportation. Now, according to the no cloning theorem, you cannot actually do teleportation like in the movies. So you cannot create a copy of a particle, of a quantum, and then send it to somewhere else. But you can transform and transfer its state. So this has been done before by Chinese astronauts in June 2017. And the connection was between Earth and their Mischius satellite, which is a distance of 1,400 kilometers. One of the photons, I think it was a pair of photons, was in Tibet, and the other was at the Mischius satellite. And they were capable of beaming or teleporting the photon to the satellite, and they were capable of measuring the entanglement by spinning the photon, for instance, and then were also able to teleport it. Now, how this works is essentially you have a pair of photons. And let's say there is Q. So Q is one of the photons that you're trying to teleport or beam. Then there is S. So S is an outside particle. And then there is T. So in this case, Q is in Tibet and T is at the Mischius satellite. Those two are the two photons and they are entangled. Now what you do is you entangle Q, which is the particle that you're trying to send, so to speak. You entangle it with S. And S is the new particle. And then you entangle S with T. This is possible because you can entangle particles more than once. And as you entangle S with T, and as S sort of transfers over to T, it can transfer over Q as a new state to T. And thus you can effectively teleport Q. I hope this was sort of clear, but it's quite complex as you can see. But this is more or less how teleportation in a quantum world works.